All right, what do you say? Let's jump into some tougher algebra problems. Yes, I have given you the law of sines and law of cosines that can be used in a triangle. Maybe we'll need it. Who knows? I gave it to you on top, though, just to refresh your memory in case we do need it over the course of today's lesson. All right, hop right into it. Number one, find x. That's a chord, isn't it? That's a chord. I can tell you guys right now, you cannot find that chord just based on the information I've given you. Just that diagram all by itself is not going to help us out at all. The segment that I have labeled 3 units, what's that called? That segment that's labeled 3 units. 7, that's Tyler. That's called a radius. Great job. That's a radius. So that means if I draw in another one, how long is it going to be? 3. If I draw in the second one, how long is it going to be? 3. 3. All right. And does anybody see any fact from yesterday that's being applied here? Yes. With that right angle symbol. What's happening? Tell me something that's happening in this circle based on a fact from yesterday. 12 spot. Zach, see what's happening at all? Any facts from yesterday?
Sorry, I was trying to turn in the homework and just got my paper out. Can you repeat that?
Okay, on number 1, I have this length of 2 that's perpendicular to the chord. Tell me something that's happening then to the chord from yesterday.
Oh, the chord's getting bisected.
There you go. So, hey, guys, at least we know this piece is equal to this piece. So if you could find that, then I could double it and we'd be all set. Okay. Keep talking to me. Anybody want to keep chiming in? Tyler, go. Got a suggestion.
So we can form a right triangle using the radius of 3.
Yep.
And then you can use the Pythagorean theorem to find the answer.
Good. All right. So we got one radius of 3, meaning if I draw in another radius, say that one, that forms a right triangle, we also know that's 3. And now, yes, I can use Pythagorean theorem and double my answer at the end. This is what you can start to expect now, guys. All right, problems like this where it's a little bit more challenging. You need to add some parts to the diagram. So I got a squared plus b squared equals c squared. Let's see, one leg is 2. The other leg, I'm not going to call it x because that would not be the whole chord length. So I'll just keep it b squared equals my hypotenuse 3 squared. Okay, let's solve for b. Question to everybody. Is b going to be my final answer? No, I asked that because I don't want you to round this. You should not be rounding the square root of 5. You should be leaving it right in your calculator and then doubling it right there. So you're going to do 2 times radical 5, actually, and then you can round it. All right, so make sure you don't round radical 5. That's not my final answer. Double it right in your calculator, and then 5.5. Questions there from you guys? All right, so this is what we're starting to work with now. You know, a little bit different than your homework where it was just, hey, I'm just going to set these 2 equal and I'm on my way. Got to do a little bit more work now. All right, 2, a little bit different too, as well. Wow. Doesn't look like I gave you anything. And if anybody's confused, x is the length. I'm looking for the length of the chord. That's x, the length of the chord. 120 is the measure of the arc underneath it. Looks like one radius is 12. Oh boy, does not look like I gave you much there. I didn't, in fact. What do you think here, guys? Anything you want to try to add in? Tim, what's up?
You could say the chord is 120.
Oh, no. No. Chords are not equal to the arc measure. Not equal to the arc measure. All right, not equal. I am going to use that 120, but not on the chord, though, eventually. Oh, I got a ding. Let's see who the ding is here. Eric, what's up, stud?
We can connect the center point to the other point.
Sorry.
The other end of the chord and call it a central angle and give the angle 120.
Okay, so you're saying make it into a triangle, right?
Yeah.
Okay, yep. So here's what Eric is saying. He's like, hey, I can draw in another radius that I definitely know is 12, and I form this triangle right here. Let me blow it up. 12, 12, trying to find that side. And I don't know if anybody heard his last part there, how he's going to incorporate the 120 degrees. Sarah?
This is a central angle.
Yeah, this is a, hey, everyone take a look. This is a central angle, right? And we know that's one of the first facts we learned. A central angle is equal to its arc measure. So if the arc is 120, the central angle is 120. All right, good job, guys. Good job. We're getting there. I don't know what else. Is there anything more I can add on, or do we see something maybe I can do to find x?
Law of cosines. Maybe.
Okay, Tyler in class is saying I could use the law of cosines, which is true.
Actually, maybe we should use the law of sines.
All right. Okay, now he's saying use the law of sines. I don't know where he's going with this, but if you want to use law of sines, you need two angles. I only have one.
Yeah.
What? Can you get me another? Sarah, what type of triangle is it?
Isosceles.
It's isosceles. Guys at home, you see that? It's isosceles. And we know this year, across from the congruent sides are congruent angles. Somebody help me find what the angle should be then.
The angle should be 30.
30, correct. I had 60 left over divided by 2. This is not a right triangle, so Pythag, out the window. I can use law of sines. Anytime you have 2 degree measures or more, you can use law of sines. Tyler was right at the beginning. Before we found the 30-degree angles, we could have used law of cosines. I just figure law of sines is a little bit easier on everybody, but law of cosines would have worked before we found the 30s. All right, law of sines. I need a side over an angle. Give me a side and an angle relationship here. Side and an angle that you know. 8. Shen, here we go, Shen. Give me an angle and a side relation you know.
And the angle could be 30 degrees.
Yep, a side across would be what?
12.
Okay, so I'm going to start 12 over. Hopefully you guys remember I'm not going to put 30 on the bottom. Law of sines, sine 30. And then what should be my other side and angle relation on the other side of the proportion? 18. Sean, what should be on my other side now?
X
Yep.
over the sine with 120.
Good job, Sean. All right, there it is. Guys, I don't know how many of you have screwed around in your calculator on Radians Day. Make sure it's in degree mode constantly. There is no reason this year in geometry you need it in radian mode. Keep it constantly in degree mode. So sine of 30 times x, I'm cross multiplying, equals 12 times sine 120. And then, yep, you can solve for x by dividing both sides by the sine of 30. And then round to the nearest tenth when you get it. Woo! I love these. These are definitely honors, right? Honors level problems. You got to know facts about a circle and then just start applying stuff and see what sticks here.
Will the law of sines or cosines be given on the test?
No. The only thing I'm giving you is what's on the formula sheet, which is radians to degrees and degrees to radians conversion. Okay, so you should, what do we got, 20.8? Okay, please stay on this problem. Please stay on this problem. Because I do not want you to get in the mindset that you had to do this using law of sines or cosines. You did it. You didn't. Watch, kids. Let's say you just didn't think about law of, maybe, or you forgot what the law of sines was and you're not comfortable using it. You could have drawn your own perpendicular radius down bisected that side. Anybody know what type of triangles I've just formed on the left and right here?
2 right.
A right triangle, but more specifically, that's 30, that's 90, that's got to be 30, 60, 90. So if you remember your rules, you can use it there. Also, a right triangle. SOHCAHTOA could have been used. Sine, cosine, tangent. A lot of different ways. Okay, a lot of different ways I could have gotten to that. Questions at all? So I think there's one on your assignment this weekend that you're going to have to play around with a little to see what works for you. All right, I feel like I need some hype music now.
Oh, we're doing
We're back.
the
We're back. We're back. For the first time since product of the means equals product of the extremes, we're back. Yes! It's been so long. I feel like my excitement level is not being matched by my students, but that's okay. I'll work on it.
I think I know.
That just takes me to another level now.
I know how to start this.
Arc AC is congruent to arc CB. So the two arcs are congruent. I am asking you to prove the two triangles congruent. Before we do that, we need a little refresh. We need a little refresh in proving triangles congruent. 5 ways. What do you got? Let's read the classic first one you ever learned.
Side angle side.
This is only if what?
The angles in between.
Angles in the middle.
It's for proving triangles congruent.
Like,
Correct. There's two
Angle.
2 out of 5.
Angle.
40% honors.
Angle side angle.
Angle side angle.
Angle, side.
Yeah. What if it?
Triangles.
Whoa. That's unbelievable, Mr. Carlino. You should be ashamed of yourself. I have no idea where that came from. That's a slip. Angle side angle, and the one I'm recording too, so you get to live that
Oh.
forever. All right. If you want.
Hypotenuse leg.
Hypotenuse leg. Good. Only in what type of triangle though?
Right triangle.
Right triangle. Wow. I'm embarrassed. I'll get over it. So those are our 5 ways to prove triangles congruent. So if you know the arcs are congruent. Now, before we start, do not think you just have to use circle facts and that's it. We've had 7 months worth of geometry facts that you could use here. Do not think every single reason has to be a circle reason. It could be something we've used in October if it gets the job done. Proving the triangle's congruent. Here we go. Name a pair you know that are congruent. Angles or sides. Name a pair. Number 1, Sarah.
Both the central angles, so AOC and COB are congruent.
All right, we have angle AOC congruent to angle COB. Good work. That gives you a pair of angles. Now, what would be the reason? How does Sarah know that? What told her the central angles were congruent? Because they're not congruent unless something happens. What was given?
Congruent.
You're good. Congruent arcs imply congruent central angles. And it is important that you have the word central in there. If you just say congruent arcs imply congruent angles, that is a false statement. False. It only implies the central angles are congruent. All right, thanks, Sarah. She got you a pair of angles. Somebody going to get me another pair of congruent something. Oh, 1, 5. Here we go. Provide. Anything else up here congruent?
You could say OC is congruent to OC because it's reflex.
There it is. Our good old friend, everybody. The OC. Congruent to itself. Like I said, you have everything available we've learned the last 7 months. You don't just have to have circle facts. There's a side. Ooh, it looks like we need maybe one more pair. One more pair. One more pair. Got another pair up here for me? Oh, whoa, whoa. Eric, Got another pair?
You can say OA and the OB are congruent.
Good job, young buck. Good job. OA, congruent to OB. What are those that Eric just gave me? Radii. Remember, we just went over a ton of algebra problems where the radii are always congruent. So what we were I know we only wrote it once yesterday, but ready? In a circle. That statement's got to be there. Because if you write all radii congruent without that, that's not true, right? Or every single radii congruent? No, only in a circle. The same circle. In a circle, all radii are congruent. And that gives you another pair of sides. And what do I have here now? Triangle BOC, congruent to triangle AOC, a little thing we like to call side angle side.
We've also done side because line AC is congruent to line BC because the
Let's not call them lines. Let's give them a proper name.
chords.
Chords, yes. So if anybody at home was waiting for their number to be called, and maybe you were going to tell me that chord BC was congruent to chord AC, you would have been correct. And yes, we could have proven the triangle is congruent by side.
Is there a special symbol to denote a chord?
No, you just write line segment. Yep, line segment, just like the radii.
Cool.
Other questions from you guys at home? Anything? What's that? What? Oh, you're hungry for another one? You got it. Let's eat. Here we go.
Okay.
Oh. Circle O, so O must be the center. Radius OC, ooh, is perpendicular to chord EF. So I got a right angle action, huh? All right, before we start, look at what I'm trying to looking for you to prove. The angles are congruent. Prove those two angles. Wait a second. Back in the day, I remember something about you can't prove the angles congruent unless you
Say there.
prove the triangles congruent. What was that little thing called? Proving the triangles and then the angles? CPCTC.
I remember that on the test. I was like,
CPCTC. That's what proof this is going to be. But even before we get there, we got to prove the darn thing's congruent. Okay, help me prove the triangle's congruent right now. And again, circle facts or anything we've learned in the last 7 months. Hey, I'll give you a second to think before I call on you. What up here in these two triangles could you prove congruent? 7, Tyler, where do you want to start?
Can I say two things that go together? Okay. So angle EWC and angle CWF are right angles, and then the next one would be because they're right angles, they're congruent.
Okay, so what Tyler is doing, he's like, all right, I remember back in the day, you could not just say right angles were congruent right away. You first needed to tell me that they are right angles. So angle EWC and angle CWF are right angles. Perpendicular lines form right angles. And then, yes, saying that they are congruent. Thank you. So that gives me one pair of angles on the board. All right. Anything else you know are congruent up here? Anything else? Oh, geez. Liam, go ahead.
I was going to say that EW is congruent to WF.
Okay, I'm glad you said that. Now, Liam is correct, but not right now in the proof he's not correct. Here's what I mean. Liam, I'm going to go back to you. What made you say those two segments were equal?
Because the chord EF is perpendicular to the radius OC.
So what's that mean based on that theorem? If they're perpendicular, what happens?
The radius bisects the chord.
That's what it says. The theorem at the end says the chord is getting bisected. It doesn't say at the end of the theorem the two segments are equal, does it? All the theorem says is the radius, OC, bisects the chord, EF. I want to make sure you use that theorem appropriately. The theorem does not say these two segments are equal. We'll say that next for another reason. All right? What the theorem says is the radius bisects the chord, so that's what I write in my statements. A radius perpendicular to a chord bisects the chord. And again, instead of the word radius, if anybody wants to use diameter, go ahead. Now, can somebody tell me why I can say that EW is congruent to WF? Nothing fancy. Why are those two congruent now?
Halves of a.
Definition of a
Definition of a bisector, right? No, oh, sorry. Definition of a bisector. Yeah, nothing crazy.
So we don't have to do the like halves of a whole thing.
No. Hey, I just want to make sure this theorem is not used to say two segments are equal. It is used to say the chord is getting bisected, so please write that in your statements. That was the reason why I put this proof on your notes here. All right, so Liam got us a side. And I'm looking for one more pair of something here. All right, come on now. Come on, guys. Come on. I'm actually surprised this was left to be last. Dave, last one here, David. What's that? What else do I have?
WC equals WC.
Yeah, there you go. There's another side. And then looks like I have enough to say those triangles are congruent. Remember, order of the vertices matters. Make sure you match up sides and angles when you write both triangle names. So if I go EWC, if I name that first triangle EWC, I got to go FWC in the other one. And last question as we head into the weekend, what method are those two triangles congruent? 1, 5, provide. What method do I have here?
Side angle side.
There you go. And remember, we weren't proving the triangles congruent. We were proving the angles congruent. So you do need one more step after to say angle CWF congruent to angle CEW, a little CPCTC. I'm actually interested that this is the first time I saw it here. All this stuff. Because I'm recording. I've never seen that before. How about a sticker?
You gotta put your pen on the screen.
Cool. Oh, never mind. Can do it. Let's try it. I gotta go back and.
Guess not.
What? What is that doing?
It's placing stickers.
I guess it's only on the screen you're on.
Or it could also be that that because you're using the smartboard, that has a different input. So
I think this is coming from me recording.
right, but because
No, I know, I got you. Yeah.
So like if you try placing it anywhere else on your screen, like in a different
First time this number's been on some of your papers, huh? Oh, sorry. Too harsh? Too harsh before I go in the weekend? Too harsh? You guys at home? Sorry. Too harsh? Too harsh? Sorry about that. What else do I have here? Oh, a rectangle. Wow, that's important.
put up an 80 on the screen. That's not the first result.
There you go. There we go. All right, I'm good.